So we're just going to do this one sketch and then move on to the quiz. What do you notice? What kinds of things you maybe look for when you start a sketch? Ah, good. When, if what?
If it's in like oblique,
Right, good.
there might be some it might be a factor like a common denominator.
Okay, so I like that you said factor in there because that's going to be important. What else? The degrees. So we have a 3 on top and a 2 on bottom. So what does that mean? Oblique asymptote. And because we have not a linear term in the bottom, it's bigger than 1 degree. Yeah, we would be doing long division. Good. As I've said in the past, we like to have the factored form and the expanded form of these. When we're going to solve for y-intercepts, we're going to solve for x-intercepts, we're going to solve for vertical asymptotes, horizontal asymptotes, oblique asymptote, whatever it has, right? And to do that, how do we find horizontal asymptotes? Sorry, how do we find vertical asymptotes, I meant to say?
The numbers that make the denominator 0.
Right, and so we need that to be in factored form. And how do we find x-intercepts? Set y to 0, and what does that mean? Okay. Yeah, so if y is going to be 0, that means the numerator is going to be equal to 0, so we need it factored form as well. So I'm going to do that so it's done nice and quickly. What do you mean? But we would be dividing by a factor. Are you talking about for the oblique asymptote when we do that later on?
No, I'm talking about the factors at the top.
Yeah.
How can you do that with oh, I guess you can do it the other way.
Like synthetic division, is that what you mean? Yeah, or you're going to factor this however you factor it. Whether, the bottom is just a simple trinomial, so we'll factor it that way. We're probably going to use factor theorem and synthetic division for the top, right? But to speed things up, I'm going to give you the final version. So this would take a couple more steps than this. You wouldn't typically be able to do this in one step. But we need it, both the top and bottom, fully factored as we can get them. Okay, now what do we notice? Yeah, there's a hole. Why do you say that, though? Yeah, there's an x plus 2 on the top and the bottom, so they divide to 1, and that means we have a hole. Hole at x equals -2. Okay, so we'll remember that and hang on to it for later. So I'm going to rewrite this. And we are going to want the expanded version as well of this. So we might as well do it now so that all of that is done and out of the way. And we still see, it's not going to change the fact that the top is exactly 1 more degree than the bottom. It's not going to change that fact, right? Because we're losing a degree in both. So it's still oblique asymptote. Okay, now we can move on to our intercepts. If you've been doing the practice over the weekend and along the way, you probably have noticed that it really does help with these long processes to have some kind of order that you get used to doing it in. Not everybody quite does it this way, but I like factoring it all at the beginning, because once you get into it, once you're finding the x-intercepts, you need the top factored anyway. You're basically going to do it right away. So it's nice to start with that, get all our different versions written up, and then move in whatever order you do, doesn't matter, but I do intercepts, then asymptotes. Okay, so the y-intercept occurs when, how do I find the y-intercept? Yeah, so when x is 0, so 3 over 1, which is 3. And the x-intercepts, we talked about this, but negative 3. And where'd you get that from? Yeah? Like this? And that? Do we only have one? We have two, and they are 1 and 3. Good. Positive 3, not negative 3, right? Good. Yeah. When the top is 0, like we already discussed, but top is factored. We've got a factored form, so it's easy to pull out the x-intercepts. Are you going to say something?
So when there's a hole, it's not an intercept.
Correct. Yeah. Graph doesn't exist at a hole, so it can't be an intercept. It would be both. It would have been both an x-intercept and a vertical asymptote, I guess. I don't know. All right, what else? I think that's good. We'll move on to asymptotes. My vertical asymptote is x equals negative 1. Thank you. We only have one. In this case, it looked like we were going to have two, but we only actually have one. It makes our job a little bit simpler, a little bit less work. How do I test around asymptotes? Folks, you got to visualize this stuff. You got to think about what a vertical asymptote looks like. Think about what x is doing as you're getting close to that asymptote. There's 3 different tests around asymptotes. And they all have their similarities, but they're all different, and their interpretation is different. You really got to practice this and think about this until you get to the point where you get it, and you understand why, and you can do it. So for a vertical asymptote, if my vertical asymptote is negative 1, I'm getting really, 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 really close to it. That's what asymptotes do. They get closer and closer forever, and they either go up or they go down. So I'm going to pick numbers that are really, really close to negative 1, just to the left and just to the right. So it's negative. So just to the left would be 1.001. And just to the right would be negative 0.999. And it speeds things up. It's less calculator work. You can do this some of the time. You can't do it all the time. Like for horizontal asymptotes, you can't do this. We'll talk about that a little bit later. But I can take negative 1.001, and I can just imagine the signs of each of these brackets. Right? And that's good enough. And we talked a lot earlier about making sure you get a big number when you sub in. But if you do it this way, it convinces yourself that there's no way that I can sub these numbers in and not get a negative number or not get a positive. That tells us enough about what's going on. So when I sub, this is what I'm subbing. I'm subbing negative 1.001. When I sub it into this first bracket, I get a negative minus more, so that's negative. Again, negative minus 3, that's going to be negative, so I got 2 negatives. And then this plus 1, well, the negative 1.001 wins. Right? I get negative 0.001. Like that's easy to do. I've got a negative number and a smaller positive. So that's going to be negative. So I believe I got 3 negatives there. Does that feel right? But if you don't follow that, or if you find that hard, if that's not straightforward, plug it into your calculator. It takes one of the worst things, so this one should be negative. One of the worst things you can do, folks, is sit there and hum and haw, like, I don't know, did I do that right? Is this right? That's going to waste more time than just punching it into your calculator. And that punching into your calculator seems easy, but I've talked to a few people, and they do make mistakes as they do it. Like, it does require a bit of practice. So, again, don't take that for granted. There's lots of brackets involved, that kind of thing. So make sure you've done it a few times and that you can do it consistently. And for the next one, I'm plugging in negative 0.999. So this is still negative. The top 2 are still negative because you're subtracting. But what about that bottom one? Negative 0.999 plus 1. Well, that's going to be positive. So now I have 2 negatives and a positive, which means this one will be positive. So I write out my statements. As x approaches negative 1 from the left, y is going to negative infinity. As x approaches negative 1 from the right, y is going to positive infinity. And we already discussed how we have an oblique asymptote. Is everybody okay with that? We have an oblique asymptote. So how do we find our oblique asymptote? We take this version and we actually do it. We actually do that division. So we're doing x plus 1 into x squared minus 4x plus 3. And then what do we do with that? This is a really important part of the step. I think everybody in here is very comfortable with synthetic division at this point. Remember when we learned that? It wasn't that long ago, but it seemed pretty crazy. But then all of a sudden you actually get good at it, and you're like, I'm totally comfortable doing synthetic division. That's the easy part of this question. Probably many of you feel that way. Once you get to this, you feel comfortable doing it. But then we got to know what to do with the result. So we write out the division statement, which is x plus 1 times x minus 5 plus 8. But that right there, whoops, actually just equals the top. If you remember our stuff about division statements, way back when we learned about this, this is a way of rewriting that. But we want it to be f at x, the whole thing. So what do we have to add? We have to add the bottom, which is the x plus 1. And I'm going to do it this way so I don't have to do an extra step. Yep.
You know how you said you can do the negative, just finding the signs?
Yep. Earlier on for the vertical asymptotes. Yeah. The only one you can't do it for is horizontal. We'll talk about that in a minute. Now I'm going to talk about this again, remind you what this means. Take a look at what this is, but this is interesting. Way back in grade 9, you learned about lines, and you learned about how to put the equation of a line into different forms. Y equals mx plus b, which is super useful. It's good for graphing. It's good for plugging in x's and solving for y's. It's good for all kinds of things. Standard form, which is pretty useless, but it at least gives us something to do. And gives us a chance to practice our algebra, which we need lots of practice of in grade 9. So, and you convert it back and forth. You convert it into whichever form is convenient, I suppose. Then we get to grade 10, and it's even more interesting because you're often given standard form of a quadratic. We can actually see why standard form of a quadratic is useful, right? The fully expanded form, because for when we're solving, for factoring, that kind of thing. But putting it into vertex form is really good for finding maximums and really good for graphing, and then factoring is good for solving and finding x-intercepts. So we have these different forms, and you learn about how to the tools that are required, like completing the square, to take something and put it in a different form so we can get the information out of it that we need. If I'm solving for the x-intercepts where the ball hits the ground, I want to put it in factored form because that's what's going to be useful. This is exactly what we've done here, folks. This is a strange way of writing the original function that we got. But this is absolutely the exact same function as the original version. And it's just, we've written it in a way that gives us the asymptote where I can pull out the information I need in order to sketch it and figure out what's going on around that oblique asymptote. Right? So this is a very, it's a bit of a interesting idea and a bit of a strange result in some ways when you think about it. And in the end, if you're not totally getting it, I mean, you can just do the steps. You can just kind of memorize the steps. And that is your oblique asymptote. If you're not really sure why, it's not the end of the world. You can still do this. And that is the remainder part. And if you're not really sure why, I mean, you can still do it, right? But it's interesting that that's what we've done. This is another tool in our tool belt to take something and put it in a new form to get the information we need out of it, just like completing the square factoring, that kind of thing. Isaac, did you have a question? So remember why this is useful. As x gets really, 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 really big, this thing gets small, basically becomes 0. And the whole function looks basically like that. So x minus 5 is our oblique asymptote. That's what the graph more or less looks like as it goes way off to the left and to the right. But this isn't, it's not 0, it's just basically 0. If it's positive, I'm taking that line and adding a little bit. So that tells us where the graph will be. If the remainder part is negative, I'm taking the line and subtracting a little bit. So I know where my function will be in relation to the oblique asymptote. Okay, so then we're going to write this out. The oblique asymptote is y equals x minus 5. And I'm going to think about the slope and the y-intercept as well, because that's how we're going to graph that. And then the remainder part is r at x equals 8 over x plus 1. And how do I do the testing for this?
1,000 negative.
Yeah, I'm going to put in like a big negative number. And again, you're noticing that if you're getting this, you're noticing it doesn't really have to be 1,000. Negative 100 would work, because when I put it in, this is 8 over negative 999. So that's negative and small. It's like 0. We checked this morning. It's like 0.008. So you're negative. So you're taking x minus 5 and you're subtracting a little bit. So where are we? So this is negative. Therefore, what? We're below. And that's what we need to know. And again, 8 over 1,001 is positive. Therefore, we are above. And now I think we have all the information we need in order to graph. Any questions before we move on? Yeah.
Clarification, when you have an oblique asymptote, there is no possibility of a horizontal.
Correct. All right. Yeah.
Is that because it's like something over 0?
Well, right. If we tried to find a horizontal asymptote and you're looking at the coefficients, the bigger coefficient is on top. So it'd be like 2 over 0. So yeah, you're never going to get one.
Are you sketching?
Yeah. No. Well, not like this.
Is that why you're using a different program?
Yeah, it's a different version of the same program. For some reason, they have 2, and they each are missing things that the other one can do. For some reason, hopefully, Microsoft is working on that. All right, we only have one vertical asymptote. And I have my oblique asymptote. I'm going to do my intercepts first. So I have a y-intercept of 3 and an x-intercept of 1 and of 3. Oh, and I want to label those. I'm going to pencil in the behavior around my asymptotes. So as I approach -1 from the left, I'm going to negative infinity. So that's here. And as I approach -1 from the right, I go to positive infinity. So that's here. As I go out to the left, I'm below the oblique asymptote. And as I go out to the right, I am above the oblique asymptote. And this all makes sense. Sometimes with these, it can be hard with the oblique asymptote. You only end up with this little corner, and I knew it was coming. I tried really hard to give myself some room here. It doesn't matter if this part ends up being ends up kind of just going like that, and you don't have a lot of room. That happens. But this one's going to kind of go like this. Hold on. Yes.
How do we show the whole?
Good job. You didn't even let me pretend to forget about it. Usually people forget about the hole. And so where is the hole? You thought about it before we even finished the graph. The hole is at x equals -2. So let's see how we draw the hole, because it is right here. The asymptote is at -1. So I go to -2 and I literally draw a hole. And it doesn't have to be where it's turning. It kind of works out that way here, but it doesn't have to be like that or anything. It's not like it's at that maximum point or anything necessarily. And look at how all of this fits and makes sense where I am, oops, I undo that. Where I'm coming down from here, I'm going through my y-intercept, I'm going through my x-intercept, and coming back up. If there was only one x-intercept, it would have to be a turning point on that x-intercept. But because there's two, I know that it cuts through. And there we have it. There's our graph. Any questions?